Hey, what's up, guys? So this is my second video about analytic number theory. And previous we already give the highlight of analytic number theory. Basically, you start from this differential series and then connect this function lambda function with the zeta function. Now you do the main transformation and the Perron's formula and pick out the roots and the residue. Then you can prove the prime number theory. Okay, but there's a detail that I haven't, there's a subtle detail that I haven't talked about is that, simply speaking, if you want to prove this prime number theorem, you need to show the following. Okay, you need to show the detail. You need to show, so this is the, you need to show the zeta function has no zero when real s greater or equal to 1. Okay, so simply speaking, you need to show this function is non-zero if real s greater or equal to 1. Okay, so this is an interesting thing. You need to spend a little bit of time trying to prove this. Okay, so this is our goal today, and I also I will prove another thing which is not important, but the one can prove that at the s equals 0, there's no zero for zeta function. Okay, so this is zeta t. So zeta it is non-zero for t is a real number, and the zeta s is non-zero if real s greater than 0. Okay, let me just give the proof. So theorem 1 is zeta 1 plus it is non-zero. Okay, so t is a real number. Well, this proof is very standard, so let's quickly prove it. So there's a lemma which is very simple. You start from 2 plus 1 plus cosine square to this is greater or equal to 0. So you can expand it and use the double angle formula. So it's cosine 2 theta plus 4 cosine theta plus 3. Okay. Now you can write zeta sigma plus it. Let's say sigma is greater or equal to greater than 1. Let's take a real number sigma greater than 1 and consider this sigma plus it. Okay, and you can use the Euler product formula. So it's 1 minus p minus sigma minus it minus 1. Okay, and now use the let's take a log, right? So you can take a log. You get log of zeta sigma plus it equals to minus 1 summation p 1 minus p minus sigma minus it. Okay, and there's a log here. Okay, now you expand it. You get the summation of p, which is our prime number, m from 1 to infinity 1 over m, and the p minus m sigma minus imt. Okay, let's take the absolute value. Okay, this is a simple if I take absolute value, let's say I take this, and I will take absolute value of this, right? So it's summation of p, summation of m from 1 to infinity, 1 over m p m sigma. If I take the absolute value, then I get cosine term, right? I get cosine term, so I get cosine mt log p. Okay. Hopefully this is simple. We just change it to just exponential ix equals to cosine x plus I sine x. Okay, hopefully it's not difficult. And once you've done this, let's remember this. Okay, once you've done this, then let's consider 3 log. 3 log zeta sigma plus 4 times log sigma plus it plus log, sorry, not sigma, this is all, sorry, this is all delta. This is all zeta function, sigma plus 2it, take absolute value. Okay, so once you do this, so sorry. Okay, so it's zeta function sigma plus I 2t. Okay, so you do this is cosine to zeta plus 4 cosine plus 3, right? So you get this, right? So you get 3 cosine terms. Okay, so you can simply write MP and from 1 to infinity, 1 over MP sigma M times 3 plus 4 cosine MT log P plus cosine 2MT log P. Okay, greater or equal to 0 because this term is greater or equal to 0. Okay, so combine everything, which we get the log of zeta sigma cube, zeta sigma plus IT absolute value with power 4, and log of this. This is not log. This is just another log zeta sigma plus 2IT. Okay, these terms greater or equal to 0, which means that these terms greater than 1. Okay, greater or equal to 1. Okay, so we got zeta cube, zeta sigma plus IT to the power 4, zeta sigma plus 2IT greater than 1. Okay. Okay, for every t. Okay, so now let's prove by contradiction. Suppose there are some points that zeta IT is 0. Okay, so suppose there are some there is some t, there's a t0 such that this is 0. Okay, then you can just fix t0 for this, and then just take zeta sigma approach to 1, right? But this guy is greater or equal to 1 for every t. So if this guy is 0, then it's contradiction, right? Because we know that zeta function is analytic on only for except for s equals 0. So if sigma approach to 1, that this guy becomes 0, then you get 0, then you will get 0 greater or equal to 1, which is contradiction. Okay, so this is a proof. Okay, so yeah, so this proof what? This proof that the zeta s is a non-zero for real s equals to 1. Okay. Now the second theorem is not also simple. This one I intended to just quickly prove because it's not difficult. So it's non-zero for real s greater than 1. Okay, so this one you need to do a little bit of work, but simply speaking, that let me just quickly give you the highlight. So the highlight is that there's a theorem says that if summation an converge, then the summation the product of n from 1 to infinity 1 plus an converge, and also this is the first things. Also in this case, if let's say these products convert to 0, if and only if there is a term 1 plus an is 0. Okay, so once you have this powerful theorem that you can easily prove, right? You can easily prove show these results because your zeta s has this 1 minus p to the minus 1, right? So this is the all your products. Okay, so once you have this Euler product, then obviously that you can prove this guy's absolute converge, right? By previous, you can. This is just simple the P series. Okay, because this is just this. Okay, so simply speaking, you know that if you take the zeta s, that's equal to summation n from 1 to infinity 1 over n to the real s, which in this case I choose greater than 1, right? So this guy is absolute converge. Okay, so since it absolute converge, so it satisfies this property, and so I only need to check that 1 plus an is non-zero for every term. which is trivial, right? Because I get all the products, so trivial. Things 1 minus p to s is non-zero for every p. So this guy is non-zero. Okay, so this is very simple. And the final results that I want to show is that zeta I t is non-zero. Okay, so basically I just show that I want to show that there's no zero at s equal to 0. Okay. Okay. So proof. So this proof just using the analytic continuation. So let me just write down a functional equation that I might prove in the next video. But let me just do this. Okay, so let me set s equals to it. Okay, and what? Okay, so let's say that let's plug s equals to it. Okay, so I get something here. Okay, so this part, whether it's non-zero or not, I don't know, right? But I know this guy is non-zero. This guy is non-zero. Okay. And also for this car, I know this is non-zero because this is pi to something. And I also know that this is non-zero because gamma function is only 0. Gamma function has no zeros. Okay. So then, and also this is non-zero, right? By my previous results. So by my previous fact that I just proved that zeta function is no zero when real part equals to 1. Which proves that which gives the fact that the zeta it is non-zero. Okay, because all these are non-zeros and all these are non-zeros, so zeta it is non-zero. Okay, so yeah, this is the simple fact of the zeta function. And then once you have this, then go back to the prime number theorem proof. It's just one line. You just write down everything and then doing the parallels formula. You're done once you solve this. Okay, so finally, in the next video, I will give the quicker review of the zeta function and do some analytic continuation and give you the background. I think this is enough for the prime number theorem in my analytic number theory lecture, and hope you guys subscribe to my channel. See you.